Okay, good morning. Today we will just continue with where we ended last week. So we talked about the synthesis-based architecture design process, which is an example of a domain-driven architecture design process. We took as an example the portable storage container for which we had to design an architecture. This was a project together with Philips and University of Twente, my former university. In the synthesis-based architecture design, one of the key processes was technical problem analysis. It's where we try to identify the problems before we start with the solution domain analysis. Okay. So the technical problems, the key concerns, which we could derive from several sources. One source was the requirements, the stakeholder requirements. A source from the domain, we can derive concerns from the domain. Okay, and the third one was based on quality. Okay. By looking explicitly at these sources, so stakeholders, domain, quality, we ask questions to derive the essence of the problem. Okay. So this is a step after the requirements analysis. So a step between the requirements analysis and domain analysis. Then we derive these problems, and this was the result of the problems, the top level view of the problems of the portable storage container. So we identified 9 key problems that need to be solved to define the software architecture. Okay. Once we know the problem, we can start with the domain analysis, solution domain analysis. Okay. Any questions about this? Okay. Domain analysis or solution domain analysis, to make explicit that we focus on solution concepts, the concepts that we are going to map to architectural components. This is a short summary. What's a domain? An area of knowledge, as we have seen last week, characterized by a set of concepts and terminology understood by practitioners in that area. So we have to, in the domain-driven approaches, also in synthesis-based architecture design, we have to analyze these domains to derive the key concepts. And for that we have defined or discussed the definition on domain analysis, which is the systematic activity of collecting, organizing, and storing domain knowledge. Okay. Domain analysis is really a key process in different disciplines of software engineering, including software architecture design, but also product line engineering, model-driven software development. Actually, this is one of the key processes. In software architecture design, we try to identify, we do domain analysis to identify domain concepts, so that we can map these to software architecture. And the key idea was here, the domain is stable. So if our architecture is based on the stable solution domain, then the architecture itself will also be stable. So that was this story. So includes solution concepts, provides a solid basis. We have discussed this actually last week. And in domain analysis there were, so to remember, there are 2 key issues, two sub-processes, domain scoping and domain modeling. In domain scoping we try to characterize, identify the relevant domains and the knowledge sources. In domain modeling we map this to some tangible format, so representation. In domain analysis, in the synthesis-based architecture design, the acronym is SYNBAD, it's like this. So for each problem, sub-problem, identify and prioritize the solution domains. So we did a problem analysis. The problems define actually where to look at. So we take each problem and try to identify the related domains. Once we know the domains, we identify and prioritize the knowledge sources. So this is the scoping. And once we have the knowledge sources, we extract the domain concepts, structure these, and model these. If needed, we define the solution domain concepts. If the domain is quite large, very large, a sub-domain concepts can have an internal structure itself. So we just refine the domain concepts further. Okay. This is the case. So we identify the problems based on the stakeholder requirements, based on the problems in the domain itself, and based on specific quality concerns. Every problem, to solve a problem, there's some domain, a solution domain. Therefore the term solution, because it provides a solution to some problem. Problem includes set of solution domains. Solution domain includes knowledge sources. This is our solution domain in our case, ambient intelligence domain, in particular the portable storage devices, that's the domain. And there are plenty of knowledge sources which we identify, prioritize, and once we have this we can define the concepts. So what's the process? It's quite easy actually. Once we have the fundamental concerns or technical problems, we search in the domains. And for that actually, so we take one problem. The classification, the taxonomies of these domains can help us to identify the relevant domains. If you are an expert, a domain expert, or if you have a domain expert in your organization, it's very often more easy to identify the relevant domains. Okay, they can just say, this is domain that's required. But if you are not an expert, so typically then you have to find these domains yourself. And the process for that is not that difficult. Actually, so we look at the domain from the perspective of problems. Okay? So that's also one of the important benefits of problem analysis. Otherwise, we would have requirements analysis, domain analysis. So, but where to look at, right? So technical problems actually also help to scope the domain. So you have you start with the requirements analysis. The domain to solve, to provide the solution to the requirements is quite broad, very broad. So what we do there is to identify explicit problems. And this is the first actually gross-level scoping of the domain. The problems, and in this case, these were the top-level solution domains that we identified. So connectivity, storage, environment, multimedia retrieval systems, multimedia asset usage. This could be maybe classified together. Digital rights management, user interface, personalization, shared application, system management, business economics, production management. These were the identified solution domains. What's a domain? An area of knowledge. Okay, so we can just collect some, for example, about connectivity. We can identify dozens of knowledge sources about connectivity. And connectivity is an important solution domain for us. So what we do here is match these problems with the solution domains. So we have a problems, for example, how to exchange assets. Typically, for that, to solve that problem, we need to look at connectivity and digital rights management plus user interface. This was done in the project like this. How to store assets, the solution domain is storage, acquirement. How to retrieve assets, multimedia retrieval systems. What you see here is that the terms that we can identify in the problems very often also occur in the solution domain. Okay? So actually we try to find a match, but this is not necessary. You could have also different terms in the problems. Once we have these solution domains, we identify the solution, the knowledge sources, as we said. Okay, that's the domain analysis that we have seen. Knowledge sources, the literature, human beings or existing systems. And this is the knowledge sources for the overall domain. So we prioritize, list them. KS means knowledge source. For overall domain, method for modeling ambient intelligence applications is a technical node. GK is a modeling specialist. This is a person in the organization. RD modeling specialist person. PSC issues and opportunities. There's a technical node which was considered quite relevant for designing this PSC. MIME architecture, ozone technology, etc. There's a PhD thesis that was found relevant. Context-based browsing, etc. So these were an example set of the knowledge source for the overall domain. Okay, sure. We have also solution domain for the separate problems. Connectivity, okay, was one problem. For that we look again, what are the connectivity was a domain. For this domain we could identify these knowledge sources. Networking technology, presentation, technical node, computer network, it's Dutch, so computer networks from Tannenbaum. There are some readers, etc. Solution domain. So for each solution domain, we try to identify these knowledge sources. Again, this is, as you can see, can be presentations, technical notes, papers, book, and of course we have evaluated, or these knowledge sources has been evaluated. I didn't do it myself. By looking at the abstraction quality, is it relevant and is it objective? For personalization, the same. Again, and together we have a list of knowledge sources that are relevant to design the PSC system, the architecture of the PSC, personal portable storage container. Okay, then what's the case now? So we have a domain, the PC, this would be PSC system, includes knowledge sources, and we try to identify the concepts. Okay? So how do we identify concepts? Remember, what's the process for that? It's just there, or what was the process for that? We have 10 knowledge sources. How do you call that? Everybody tries not to look at me, but how do we call that? Or what's the process? What do we do there?
We choose the relevant ones and the ones which we can trust.
Mm-hmm. That's the evaluation. So I have five knowledge sources. What do I do to define the relevant concepts? Okay, here is one process. I take one knowledge source, I throw the other, so I just look at the knowledge source there. Is that the process?
No.
Now what do we do?
We evaluate each of them.
Sorry?
We evaluate each of them and choose the most.
Right. And we look at the common parts. Commonality analysis. It's quite simple. You just look at them. You scan through all these knowledge sources and you look at the common concepts. Okay. Then we get these concepts. But every knowledge source can also have very specific concepts described. Of course. But if you look at the overall set, the set that we have, and if some concepts occurs in all these cases, so this the required domain, this just provides some raw data, but we look at the commonality analysis. We have 5 knowledge sources, we look at each of these knowledge sources. And if some concept is appearing in each knowledge source, then we say this is a common concept. So after a commonality analysis, in the domain analysis process, we could identify these solution domain concepts. These concepts were just derived by this process, quite simple. We had the knowledge sources, then look at each of these concepts, and then we said, okay, these are the common concepts. For connectivity, we could find communication manager, network model, storage, content manager, retrieval, content manager, context model, location description, shared application, communication manager, system management, cyber manager. So these were the common concepts that were derived after a commonality analysis to the selected knowledge sources. Knowledge sources that are in the set of domains that were defined based on the technical problems, concerns, right? What do we do with these concepts? So in domain analysis, we have the domain scoping. We did domain scoping, gross level scoping through problem analysis. We identified the domain, we identify knowledge sources, that's the scoping, characterization. And the second part is domain modeling. For that we could define several techniques. We define in natural language, this is the domain of PSC, and it's like this and that, so just textual natural language. Second one is to define a glossary, a kind of dictionary, where you explain each concept that have been identified. In this case, these concepts were important. Device are is a reference, defined as interaction device, mainly defined by their multimodal I/O capabilities. It can be, for instance, audio and video equipment, personal computers, cameras, audio recorders. We just give a definition of what it is. Device representation is a description of the device in the PSC. Description can, for example, contain a device entity and a description of type of device. Cybers are defined as virtual active entities representing dedicated system functionality for users. Context model, it's also interesting. It's a description of the concept, is the concept observable context. The description can, for example, contain an image of the context of the PSC, in which other descriptions are contained, etc. The details are not that important, how they have defined, but we make a glossary of our domain. Okay? Besides of this glossary, we can define feature diagrams, and another notation was conceptual model, like we have here. This was the This is the glossary. But the domain provides us the glossary, but also provides the relations among these concepts. And this was the actually eventual conceptual architecture that was defined in this project. It is simplified, but it's for educational purposes. I put it here like this. So in the system, you have a cyber manager which manages the cyber. Cyber can be personalizer or content manager. Personalizer uses context model. Personalizer adapts asset. It's very high level view, and it's also simplified. So let's look at the relation between problem, technical problem, solution domain, sub-problem, knowledge source, solution domain concept. Technical problem, solutions provided by solution domain. Solution domain includes knowledge source. Okay. And from knowledge source we can derive the solution domain concepts. The technical problem can also include subset of sub-problems, a set of sub-problems, for which also solution is provided by solution domain. Just problem analysis. Once we have the top level structure, we refine each architectural component, the concept. Actually, at this case, we have a domain architecture. We apply the same step. For each sub-problem, identify and prioritize solution domains. For each solution domain, identify and prioritize knowledge sources, problem, domain, knowledge sources. Extract solution domain concepts, structure these, if necessary, again refine. So what is refinement here? For example, asset. How do we design an asset? That's the problem. And then we do the same. What are the problems related to that? We identify the solution domains, the knowledge source, and this was the result in this case. Asset has content, has metadata. Metadata is a description. This is the overall view of the problems, the relation between the technical problems and the solution domains. At the top level we have how to design an architecture for a portable and mobile device which can store and exchange assets in a heterogeneous network environment. Solution domain, that's the top level domain, personal mobile server, and we identified 8 or 9 technical problems have been identified. Each problem had a set of related solution domains. To solve each solution domain, we can again define sub-problems. Okay, and every sub-problem can have sub-problems. In this case we had 3 levels, that was enough. Okay. So the more complex your system is, the more refinements you might need. If your system is simple, you could stop at the first level. Okay. So if you look at this, actually we can now identify two types of two ways of doing the synthesis-based design. One is the top-down, which we actually showed here. We started with defining the top-level problem and the top-level solution domain, and then tried to identify the subdomains and try to come up with the top-level architecture first. Okay. A bottom-up approach is you get these problems. For each problem you try to identify domains and then try to find the structures, the integration, the definition of top-level architecture is done at last. Okay? So that's bottom up. Usually in the project also you have to use the top-down approach. That is, you identify solution domain, then you come up with the top-level architecture. This is the case, stakeholder requirements. A key domain. So it's a domain-driven approach. One of the key domain is, of course, the application domain. Besides of that, we look at the mathematical computer science domain. These provide the concepts, and that actually provides us the conceptual architecture, domain architecture, which we will map to the different architectural views. So that's the process actually, it's not that difficult. So can somebody summarize the synthesis-based process? What did we do? So we start with requirements analysis. What do we do in requirements analysis? Architecture, what's important there? Architectural drivers, right? What's architectural driver? Concerns of the stakeholders which drive the architecture. Okay. So what's next? Then we look at the technical problem analysis. So why? So we look at problem analysis. We try to identify the problems, right? We try to identify essence of the problems, which are might not be in the requirement sense. If the requirement sense is done in a very detailed manner, they could overlap, of course. Okay? But by using an explicit problem analysis process, all these problems become explicit. What kind of problems types can we identify? Should we look at? There are three. First, problems from again, stakeholders, right? Second, problems can also be in the domain. And third, last but definitely not least, problems related to so we have only functional concerns, also non-functionals, and that's problem related to quality concerns, right? So we try to identify these problems, we list them, we have a problem model, and this gives us a nice set to scope the domain, because domain is quite large. But by looking at these problems, the key concerns, we know where to look at. We know that we need to look at, for example, security domain, okay, or connectivity domain, or storage domain, because these were the identified problems. Okay. Domain analysis consists of two key processes. What are these? First, domain scoping, right? What do we do in scoping? In scoping, we identify the domains and the knowledge sources. That's it. And modeling, domain modeling. We model the domain. Okay. That's the process. Domain-driven design. And here is domain-driven architecture design. This domain-driven design is getting more and more popular in the recent years. As I said, there's also a key reason for that. See, we reuse the domain knowledge. In our case, the key motivation was reuse domain knowledge for architecture so that we have a stable architecture. Because domain by itself is stable. So the magical word here is the word domain, the term domain. But what to do if the domain knowledge is lacking? We don't have domain knowledge. We have identified the problems, and it appears that we cannot find the relevant domains. We cannot find knowledge source, whatever. So it's a kind of engineering which requires new knowledge. What do we do? What would you do? You are a manager, or you decide.
Hire an expert in that area.
You hire an expert in that area, but there's no such an area. So there's no expert of that area. What do you do?
Divide the problems into known areas.
You divide the problems into
Known parts.
in known parts.
It should be known somewhere.
Yeah, but it's not known.
How can we design that? We cannot.
You can say this is engineering. We go beyond the limits of the knowledge that we have, the scientific knowledge that we have. We know our limits of science. We know what we know in computer science. Okay. So this is about engineering. So
We define the concepts and definitions for that knowledge, and we can create a glossary for whole team, and they can use it. We can explain the knowledge to team.
but you don't have knowledge. If knowledge, so the whole axioma is now collapsing. We say it's a domain-driven approach. We rely on domain. We can only design something based on existing domain knowledge.
We can do requirement driven approach.
No. Domain driven, but even because that wouldn't solve, right? You have you need to engineer something. You need some knowledge for that. You could say I'm going to use the requirements driven, but still will not solve. You are not forced to solve a problem which is not solvable. Can you do that? So what can you do? First, you can say, what can you say? Manager or designer. I'm sorry, I cannot solve this. There's no domain. Second, there's no knowledge. What can you do? You can try to do scientific research, right? You can try to gain that knowledge yourself. You put researches on that problem, solve this problem. Once you have solved it, you can define the design. So solution domain, if that's existing, if it's yes, that's our assumption here, then if it's sufficiently specified, then we reuse it. If not, we specify solution domain. That is, we do domain analysis, we do domain model, we define the glossary, we define the feature diagrams, we define the conceptual model, everything. So we put it. And if you are building the same kind of application every year, it makes sense, of course, to put it in a reusable format so that we can reuse it all the time. The question was, what happens if it's not existing? You said, okay, sorry, I terminate. This is not possible. A requirements-driven approach would not help here. Or you initiate research, you try to accumulate to create new knowledge so that it supports your engineering. That's the interplay between science and engineering. Domain here is just science. Engineering builds on science. Without science, there's no engineering. If science is lacking, you can say, I stop it or I create the science. That's it. It's clear? Any other options here? I don't see one. Summary. What we did, mature engineering. If we consider all these engineering disciplines, industrial engineering, electrical engineering, mechanical engineering, they are more mature than software engineering. Sometimes there's a debate on whether software development is engineering or not. To me, it's just engineering, but it's not mature yet. It's not at the maturity level that we wish yet, but it's really developing quite fast. It appears that these engineering disciplines, mature engineering, adopts a problem-solving approach. Problem-solving consisting of three key processes: problem analysis, solution domain analysis, and alternative space analysis. So every mature engineering has a process to identify and to make explicit the problems. It has a process to identify the relevant domains and knowledge source, and it has a process to identify the identified, measure, and select the feasible alternatives. We have just shown a domain-driven architecture design process, which we call synthesis-based architecture design. Synthesis is a term borrowed from these mature engineering disciplines. And the synthesis-based design process also consists of these three processes. I've explained so far. Technical problem analysis aims to identify the key concerns independent of the concrete requirements. Where we look at stakeholders, the domain and quality. And solution domain analysis, here we identify the stable domain concepts by a process of domain scoping and domain modeling. In the alternative space analysis, we will see that we will look at the architectural design alternatives and define the feasible alternatives. Questions? No questions, then we break 10 to 15 minutes.